Okay, in this video I'm going to go over Chapter 3, Sections 1, 2, and 3. I will make a separate video explaining more specific math concepts from Section 3. Alright, in Section 1 we're going to be talking about a couple of laws. Our first kind of proven theory of the atom, where experiments were actually involved instead of just ideas. And then we're going to look at, are those theories still true today? All right, so we know a chemical reaction is showing a chemical change. We talked about this in the last chapter. So we've taken a substance, we've rearranged its atoms, and we've created a completely new substance. But one thing that didn't happen was a change in mass. So we have the law of conservation of mass. Mass is neither created nor destroyed in a chemical reaction or a physical change. So if I take 10 grams of sugar and I put it in a skillet and put it on the stove and I burn it, it's no longer sugar. It's mostly carbon now. But I put a lid over it and I kept everything in there. The mass never changed. It should still weigh 10 grams. It's not C6H22O11 anymore. It's mostly carbon, and our hydrogen and oxygen have now become gas or water vapor, but we still didn't change our mass. We've just rearranged our atoms. Same thing happens with a physical change. So if I take an ice cube and I set it on a scale and it weighs 15.2 grams, I let it sit there for 30 minutes and it turns into a puddle of water. It's no longer a solid. It's no longer ice. It's still H2O. It's still going to have that 15.2 grams for its mass. All right, our next law is law of definite proportions. So if we have a compound, those elements inside that compound are going to be in the same proportion by mass, no matter how much of that substance we have. So in the example of water, H2O, for every 2 atoms of hydrogen, we're going to have 1 oxygen. And if we look at the masses of those 2 elements and we create a ratio, it doesn't matter if we have a teaspoon of water or 10 gallons of water, that ratio is going to be the same. Law of multiple proportions, we're now comparing 2 compounds that have the same elements, but they have different ratios. And so the second element that might have more of a different element than the first one, it's always going to come out with the smallest whole number ratios. So this next slide kind of explains it a little better. We have nitrogen monoxide. We have 1 nitrogen, 1 oxygen, and we're looking at nitrogen dioxide. So 1 nitrogen and 2 oxygen. So we look up the masses on the periodic table and we multiply them out. So 1 oxygen is 16 grams, 2 oxygens 32 grams, nitrogen's 14.01, and we only have 1 nitrogen in each one of those. So now we set it up as a ratio. And if you'll notice, for nitrogen dioxide, our oxygen is double the amount. The subscripts, the little numbers at the bottom, are also the lowest whole number ratios. They can't be reduced, is what that means. So law of multiple proportions, we're comparing 2 compounds. Law of definite proportions, we're just looking at 1 compound. All right, Dalton's atomic theory. So back in the 1800s, John Dalton takes Democritus's idea of the atom, and he comes up with some different postulates about it. And one thing that's so amazing about Dalton's atomic theory is the majority of his postulates are still true today. At this time in science, there wasn't a whole lot of experimentation going on. Most of science was ideas, thinking about things and saying, what if? Maybe even trying to prove them mathematically. But no scientists at the time were doing experiments. And so John Dalton's one of the first ones to kind of introduce the idea of keeping up with a lab notebook and sharing that information with others. All right, so his first idea says all matter is composed of extremely small particles called atoms. We know that. Atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. So the second one is still true. If we look at an atom of chlorine and compare it to an atom of oxygen, we know that chlorine's heavier. It has more subatomic particles in it. It's also larger because it has more rings inside of its atom than oxygen. So an oxygen atom and a chlorine atom are not going to look the same. But if we look at two chlorine atoms, they will look identical. Number 3, atoms cannot be subdivided, created, or destroyed. This has changed over time. None of these things happen naturally, but they can happen in a lab, and we know that from the atomic bomb. We also have something called an atom smasher, where they take ions and radioactive atoms and they smash them together to create new elements. And so we're kind of creating atoms there. We are creating atoms from pieces of other atoms. So this third one has kind of changed here in the last 50 to 70 years. Our fourth one, atoms of different elements combine in simple whole number ratios to form chemical compounds. This is something we just talked about with our laws of proportions. And in chemical reactions, atoms are combined, separated, or rearranged. So we're not getting rid of any atoms. We're not adding any new ones. We're taking the atoms that we already have in two different elements or compounds, and we're going to rearrange them to make something new. So the majority of Dalton's atomic theory is still true today. One thing that Dalton didn't know about were isotopes. So isotopes are atoms of the same element that have different number of neutrons. We know that neutrons are neutral. So what neutrons do is they give the atom its mass. And so this idea says that a given element can have atoms with different masses. They're talking about isotopes. All right, let's move on to section 2. So the word atom came from this Greek philosopher named Democritus. He said that if we take something and we split it in half, and we take that half and we split it in half and we keep going, we'll eventually get to something that is indivisible, something that we can't cut in half. And he called it atomos, which is Latin for the word atom. We know the nucleus, small center to our atom, it contains our protons and neutrons. Protons are our positively charged particles. Neutrons are neutral particles. Protons and neutrons are very similar in mass, so they're about the same size. We know that surrounding our nucleus and orbiting in a cloud, we have electrons that have negative charges. Electrons are so incredibly small that their mass doesn't really change the mass of the element very much. So when we start talking about ions and talking about giving away electrons and gaining electrons, the mass of our atom really won't change very much because of that. Protons and neutrons give the atom its mass. Electrons give the atom its volume or its size. So since we have these negative particles orbiting around the nucleus, those negative particles don't like to be close to each other, so they spread out as far as they can to give us that electron cloud, so it makes our atom larger. So all of these together, we refer to them as subatomic particles. So subatomic are smaller than atoms or within the atom. For this chapter, we kind of imagine these electrons on rings. By the time we get through chapter 4, we'll step away from this idea of rings inside of our atom. So here you can look at the mass of a proton and mass of a neutron, pretty close to the same. Electrons significantly smaller. We have to move our decimal 4 more times. So almost insignificant given the mass of an actual atom. So our very first ideas from Dalton is just we had an atom. He didn't think of anything smaller than that. A man by the name of J.J. Thomson, Joseph Thomson, did an experiment in the 1800s that proved that there was something negatively charged inside of an atom. He used this thing called a cathode ray tube. You can find these in old school computer monitors and old school TVs. So this is just a glass tube. It has a piece of metal hanging out of each end where it's been sealed. And inside the tube, attached to this piece of wire, is a metal disc. You can take the ends of the wire and you hook them up to a battery. Or if it's a TV or computer, you would just plug it into the wall. And then it shows a vacuum pump. So what's happened is they've sucked all the air out of the inside of this glass tube and sealed it. When you plug it in, particles, electricity, travels through the line. So our electrons flow from the negative plate and they're attracted to this positive plate. Well, when J.J. Thomson would put certain types of gas in this tube, there would be a light that would glow. And so he one day held up a magnet to this glowing light and realized that the magnet would follow the positive, or the light would follow the positive end of his magnet. And then if he flipped it over, it would move away from the negative end. So he said, okay, whatever this is has to have a negative charge in it. So somewhere in our atom is a negative charge. And this is where the very first idea of electrons came from. We have another experiment, Robert Millikan, let me go back here. He used this oil drop experiment and he came up with the charge of an electron. So they've taken this round container, almost like a small bucket, and they've cut it in half so you could see the inside. We have two metal plates inside of this container. One has a negative charge, one has a positive charge, and we do that by hooking it up to the negative end and positive end in a battery. He put a microscope in the side of it so he could look at these little bitty drops of oil. An atomizer, this sounds like something really special. It's like an old-timey perfume bottle, the kind with the bulb on the end that you squeeze to puff perfume out. He put some oil inside of a bottle and he rubbed it with silk so that it would get static electricity or static charge. And he sprayed it inside of this container. Well, these little bitty drops of oil were attracted to this negative plate. Well, he drilled a hole through the middle of this metal plate. So the oil droplets that were attracted to it, some of them fell down through that hole. Well, they didn't land all the way on the bottom. I'm sorry, this was a positive plate. They were attracted to it, so they went down. They didn't go all the way to the bottom plate because the bottom plate is negatively charged. And we know that these were negatively charged particles because they had static electricity. And so they repelled one another. So these oil droplets would kind of hover in air. So Millikan was able to take the voltage of the battery and the distance that the oil particles were from the bottom plate and calculate the charge of the electron. It's actually the mass to charge ratio of the electron. Our next experiment, go back to this, J.J. Thomson's model of the atom, you'll know it as the chocolate chip cookie dough model. So we have an atom and our electrons are just randomly scattered throughout. Ernest Rutherford had two business partners, Hans Geiger and Ernest Marsden. If you've ever heard of a Geiger counter, this is a device that they use to calculate how much radiation you've been exposed to or to even detect radiation. So if you work around radioactive elements, you have to wear a Geiger counter on your belt, and it has a timer on it, and it lets you know when you've been around radioactive materials too long and that you need to leave the room. That he worked with Ernest Rutherford and Ernest Marsden on a gold foil experiment. And what they did is they discovered that the center of an atom has a very dense positive charge that they called the nucleus. And the way they did this was called the gold foil experiment. They took a piece of lead and they drilled a hole about halfway through the center, and they put radioactive material inside there. radioactive material, this particular radioactive material, was releasing something called alpha particles. So this is positively charged radiation. So they took this piece of lead with the radioactive material in it, and they pointed it at a piece of gold foil. So this gold foil is kind of like really thin, really cheap aluminum foil, but it's made out of gold. Gold is extremely soft metal. It's even softer than aluminum. This blue thing here, this is just a screen. So they were using the screen to kind of trap the radiation. So that's these little orange things. You can see that it's the radiation that went all the way through the foil. So they were expecting these alpha particles, these positive particles, to just blow a hole through the gold foil, because they knew about J.J. Thomson and his electrons. So they said, okay, if we shoot positive particles at it, it's going to be attracted to it, and it's just going to blow a hole right through. They said they were comparing this to shooting heavy artillery at a piece of tissue paper and a shell bouncing back at them. So what happened, instead of blowing a hole through it, 1 out of every 2,000 radioactive particles actually bounced back towards them. And so these are the little ones that you see deflected off the side. So what would cause a positive particle to bounce back instead of continuing through? Well, we know like charges repel. So when these positive alpha particles hit the gold foil, most went through, but occasionally one particle would hit something and bounce back. So they figured if there was something positive, it has to be hitting something else that's positive to cause it to bounce backwards. And so they coined this positive particle as the nucleus. It wasn't later on until they figured out that it was protons within that nucleus that actually give it its positive charge. The strange thing about the gold foil experiment, they were actually trying to help support J.J. Thomson's idea of the electrons and this. They were trying to support J.J. Thomson and this idea of the plum pudding model of the atom, or the chocolate chip cookie dough model. But instead, they actually disproved them and said those electrons can't be completely scattered out if there's a positive nucleus in the center. We also know that because our atoms are neutral, when we touch things, it doesn't always shock us, that we have to have equal number of protons and electrons inside of our atom to create this neutral atom. On the periodic table, we have our atomic number, and this kind of gets us into section 3. That atomic number tells us number of protons. The number of protons never changes in an atom. We can change the number of electrons and form ions, and we can change the number of neutrons to form isotopes, but the number of protons in an atom is always the same. Nuclear forces. This is kind of what's holding our atom together. So we know we have our positive nucleus and we have our negative electrons. Well, we also have attractions in between the protons and the neutrons, and neutrons inside the nucleus. And these are called nuclear forces. And these nuclear forces are what's holding that nucleus together, and then also helping to hold our electrons in and keeping them from being attracted to the nucleus of other atoms. So when the atomic bomb was dropped, what we were actually seeing is the release of these nuclear forces. Extremely strong forces. Size of the atom. If an atom was a mile wide, the nucleus would be the size of a grape. So a grape is about a half an inch, maybe a little bit bigger than that. So if we had an atom that was a mile wide, the nucleus would be the size of a grape. Another way to think of that, if we put a quarter on the 50-yard line of a major NFL stadium, the very first electron would be out on the edge of the parking lot. Way, 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 way out in the parking lot. So we measure the size of atoms in picometers. Pico is 10 to the negative 12. So that's 12 places to the right of the decimal point. All right, section 3. So I've kind of talked about this atomic number a little bit. They use a capital Z to abbreviate the atomic number. You really won't see this again until we talk about nuclear symbols and nuclear reactions. Atomic number tells us number of protons in an atom. That number never ever changes. So oxygen is 8. It has 8 protons. If it's a neutral atom, it's going to have the exact same number of electrons. So then we could also say it's 8. That number could change on us. So isotopes, atoms of the same element that have different masses. So they have different number of neutrons. Remember, neutrons are neutral, but they do affect the mass of the atom. You are familiar with one particular isotope, carbon-14, from radioactive dating. So when they dig up a fossil and they want to determine how old it is, they can trace how much carbon-14 has decayed in it over time. And from this value, they call them half-lives, they can figure out how many half-lives it's gone through to calculate the number of years that it's been since its existence. Mass number, another value that you find on the periodic table, it tells us a total number of protons and neutrons inside of that neutral atom. This mass number can actually change depending on the number of isotopes. So oxygen, again, it has 8 protons, 8 neutrons, but it doesn't have a mass of exactly 16. That's because there's more than one type of oxygen out there. Looking to see that this is less than 16, I'm going to say that its isotope probably only has 7 neutrons in it to make it a little bit less than 16. When we talk about isotopes, we have to put some kind of value with it. That value is its mass number, and it's written as a whole number, so it's a rounded value. We can also write the nuclear symbol, write the symbol of the element. We put the mass number on top and the atomic number on bottom. So this is uranium. It's element number 92 on the periodic table, so we know it has 92 protons. And its mass number for this particular type of uranium is 235. If we subtract these two values, we can figure out how many neutrons it contains. And so mass number minus the atomic number tells us number of neutrons. Atomic number is equal to our number of protons. If we're talking about a specific isotope, we call it a nuclide. Since we don't talk about neutrons a whole lot, and we won't talk about neutrons very much after this chapter, you won't hear this word very often. So carbon-12, carbon-14, we could subtract these two values to determine our number of neutrons. I'm not going to work out the sample problems, so if you would like to stop and solve this, you should stop now and then turn it back on to check your answer. All right, atomic mass units. So this is a value given to atoms so that we can make it easier to compare sizes of atoms. Atomic mass units are all based off of carbon-12. So hydrogen atom is 1/12 the size of a carbon atom. So this is how carbon would be 12 and hydrogen would be 1. Atomic masses are all determined by comparing it with the mass of carbon-12 as well. So not only the size, but its mass as well. When we calculate an average atomic mass, We calculate it just like you would a weighted grade in one of your classes. You have to know its percent. How much is this going to count as 100? So I might say, in my class, your tests are 50% of your grade. Your homework is 30% of your grade, and your labs are 20%. So what I would have to do is I would have to take all your tests and add them together and multiply it by 50%. And then I would take your homework and add it together and multiply it by 30%, and your labs and multiply those by 20%. And then I would add those three values together. So we do something similar with isotopes. So if we go back here to this example, we have 69% of all the copper in the world is copper 63. And 30% of all the copper in the world is copper 65. So I can multiply its existence, its percent, by its mass, and then I can add the two values together to give me its average atomic mass. So see, they've taken it out of percent and multiplied it. They've taken my 30 out of percent and multiplied it, and then add those two values. And if you look on the periodic table, 63.55 is the atomic mass for copper. All right, moles. So moles tells us how much of a substance we have. Another example, we could say a dozen. If I tell you a dozen, you automatically know that that's 12. Well, moles are equal to the mass off the periodic table. So they give the example of carbon again. If we look up the mass on the periodic table, it's 12.01. So if I get out a scale and I weigh out 12 grams of carbon, that's going to be equal to 1 mole. The previous example of copper, if I weigh out 63.55 grams of copper, that's 1 mole of copper. Okay, great. You're going to tell me moles, but what does that kind of information give me? Well, if I can determine how many moles of a substance I have, I can convert it to any other type of units. I can also use my number of moles to determine how many atoms or how many molecules I have in a substance. And we do this by using Avogadro's number. So Avogadro's number, 6.022 times 10 to the 23rd. That's as far out as you have to memorize it. 6.022 times 10 to the 23rd. So if I have 1 mole of copper, which would be 63.55 grams, that means I have 6.022 times 10 to the 23rd atoms inside that mole of copper. We can also calculate number of molecules in a compound. So if I take H2O, I can add up a mass of oxygen, which is 16, the mass of 2 hydrogen, which would be 2.02. I add that together and I get 18.02. So if I weigh out 18.02 grams of water, I know that there are 6.022 times 10 to the 23rd molecules in that 18.02 grams. So what I just did, where I added the masses of my hydrogen and oxygen together, this is called molar mass. It always comes from the periodic table, and it always has these units of grams per mole. So for water, I would say 18.02 grams over 1 mole. We will use this as a conversion factor to do more dimensional analysis. So this is one of the first examples of a conversion factor they give you. I'm going to do this in a separate video to show you how to do this. So I'm just going to click through the rest of these slides. If you want to look at them, you're more than welcome to. You might want to pause the video. This mole triangle, you're more than welcome to use it anytime you want to. Some people like it, some people can't figure it out, but I'll go over it more in the next video.